Hello everyone, welcome to the course Maintenance and Testing of Electrical Machines. Lecture is Speed Control of DC Machine, week number 5, lecture number 13. I am Dr. Saurabh Kumar Rajput, Assistant Professor, Center for Internet of Things, Madhav Institute of Technology and Science, Gwalior, MP, Deemed University. The course is run by the Chhattisgarh Swami Vivekanand Technical University, Durg, Chhattisgarh, India. So, the topic discussed in our previous lecture was the starting characteristics of DC machine, and in this lecture we discussed about the DC shunt motor characteristics, DC series motor characteristics and DC compound motor characteristics. Now, the topics to be covered in this lecture includes the speed control of the DC machine, means we will discuss the different speed control methodologies of the DC machine, that is which is mentioned here in the 5 categories. The speed control versus DC motor. First we will discuss about whether the speed control of the DC motor is suitable or not. Then we will discuss the types of the speed control of DC motor. After that we will discuss the speed control of DC shunt motor, then speed control of DC series motor, and in the end we will discuss the Ward-Leonard method of speed control. So, the first topic is speed control versus DC motor, means the DC motor speed control is whether useful or not, whether feasible or not, whether economical or not, whether it is valid or not. So, considering this point, the answer is the speed control of DC motor is possible in a easy manner. That is why the point number 1 is mentioned here. The main benefit of the DC motor is that the point number 1 is mentioned here, that the main benefit of DC motor is that it has several easy way to adjust its speed across the broad range, means you can focus the two terms, that the several easy ways for the speed control and the speed control on the broader range, means all the aspects can be covered for the speed control of the DC motor. There are several methods of speed control that can provide the broader range of the speed control of DC motor. Point number 2 says, in general AC motors do not allow for such precise speed control. If we compare the DC motor with the AC motor, then such precise speed control methodologies are not possible with the AC motor. So, the DC motor speed control is easy and convenient in comparison to the AC motor speed control. And the point number 3 says, in reality accurate speed control contributes to significantly to DC motors excellent competitive position in today's industrial application. These motors, the motor which we are designing, we are talking about the DC series motor, DC shunt motor, basically the different kinds of the DC motor. These DC motors are not used in the domestic applications, because in the domestic application the supply is AC supply. These are the specific motors which are being used in the industry. So, if the motor which is being used in the industry, it should be suitable for the industrial purpose, it should be suitable for the today's industrial application, and the speed control should be the vast and all kinds of the different methodologies should be available for the speed control. So, it says that the different speed control methodologies available for the DC motor control is make it useful for the industrial applications. The types of speed control of DC motor. What different kinds of speed control of DC motor are applicable? Considering this point, there are two equations, EB, the K1 phi into N, this is the equation number 1, and the second, the back EMF equation is EB is equal to V minus IARA. These two equations, we are well known about these two equations, because in the previous lecture we discussed about these equations. Now, what we will do, we can equate these two equations, because in these two equations, both the equations are written for the back EMF. Now, equating the equations, these two equations, it will become K1 phi into N equal to V minus IA into R. Then it will become equal to N is equal to V minus IA into R divided by K1 into phi, where R is equal to RA for DC shunt motor and R is equal to RA plus R series for DC series motor. in the term where R values are different for DC shunt and DC series motor. This point need to be covered here. This point need to be explained here. The why R is equal to RA for DC shunt motor and why R is equal to RA plus R series for DC series motor. In order to explain these 2 points, the diagram of the electrical equivalent circuits of the DC series motor and DC shunt motor are shown here. In the case of DC series motor, the DC supply is connected to the series field winding, then it is connected to the armature part having the armature resistance RA. Whereas in the case of the DC shunt motor, DC supply voltage is connected in parallel with the armature and the armature is connected in parallel, or we may say in shunt with the field winding. So, this is the very basic difference between the series and shunt motor. What about the R value? What is the R value? R value is basically, if we see the DC series motor, in this case the RA and R series are in series manner, means we can say that same current is flowing through the series winding resistance and the armature winding resistance. So, these two resistances RA and R series will be considered as a in series connection. So, the total resistance will become equal to RA plus R series. Hence, it is mentioned here that for DC series motor R is equal to RA plus R series. Whereas, in the case of DC shunt motor R is equal to RA, when we are covering a complete path in the mesh number 1 in the case of DC shunt motor, then only RA resistance is coming into the picture, whereas the field winding resistance RF is in the another parallel path. So, it will not be considered. So, R value in the case of DC shunt motor will be the RA. This is the difference. So, this is the equation. This equation we found by equating the two back EMF equation, and this equation is N is equal to V minus IA into R upon K1 phi. This is equation number 1 mentioned here. This equation is very important in order to understand the different speed control methodologies for the DC motor. Why this equation is important? Because this equation is having the N value, N means the speed value, and we want to control the speed of the motor. So, in this equation number 1, we need to see that on what factors the speed is depending. N is equal to plus V means the speed is depending on the supply voltage. N is equal to plus V minus IA into R. IA is the armature current, means the speed is depending on the armature current. R is the armature resistance. It has two value, R is equal to RA plus or in other case in the DC series motor it will be R is equal to RA plus R series as discussed in previous slide, and divided by K1 into phi. In equation number 1, K1 value is the constant value, it will not play any role in the speed control of the motor, whereas phi is the flux. Flux may create a role in the speed control of the DC motor. So, if we consider this particular equation, this equation is very important to understand the speed control. In this equation, N is depending on 3 factors, and depending on the 3 factors, the 3 methodologies for the speed control of DC motor is defined. First is field winding flux control method. So, it is named as the flux control method. If the speed is depending on the field winding flux phi, the first speed control method is field flux control method. Then second is armature resistance. N is depending on the armature resistance R. So, the second method is armature control method. And the third is supply voltage. N speed is depending on the supply voltage V. So, the third method is voltage control method. So, based on these 3 terms which are depending on the speed, or we can say the speed which is depending on these 3 terms, the 3 speed control methods are defined here: flux control method, armature control method, and the voltage control method. Now, speed control of DC shunt motor. Now, we will discuss the speed control of DC shunt motor, then we will discuss the speed control of DC series motor. Coming to the speed control of DC shunt motor. The first is flux control method. There are three methodologies for speed control. For DC shunt motor, the flux control method is the first thing. Here This is the DC shunt motor, and DC, what is the equivalent circuit of DC shunt motor says? It says it will have a DC supply, it will have a armature, it will have a field winding, and all these three will connected in parallel. That is why it will become a DC shunt motor. We know all these things. Here the DC supply voltage is V, which is able to provide the current IS, supply current IS, and it is connected in parallel with the armature, complete armature arrangement having the resistance RA and back EMF EB, and this is connected in parallel with the field winding RF. What is this here? The field rehosted RE. This we have not seen in our previous cases. This we have not discussed in our previous slides in the case of DC shunt motor. This is a new thing. The field rehosted RE, which is variable shown in the nature, this is connected along with the series, along with the field winding. And why it is connected? Because we want to vary the flux. In order to vary the flux, what we need to vary? We need to vary the current flowing through the field winding. So, in order to vary this current IF in the field winding, we have connected this variable resistance in this circuit diagram. In this method, a variable resistance RE, the field rehosted, is placed in series with the shunt field winding as shown in the figure, and based on this, the flux, we can say that the flux which is depending on the field current IF, and the IF value will become equal to V upon RF plus RE. Why the IF value is V upon RF plus RE? Because if we consider the current IF in the circuit diagram, this current IF is flowing through the field winding. I is equal to V upon R is a very simple formula. What will be the voltage across this field winding? The voltage across this field winding will be the voltage across the supply, because the three branches are connected in parallel. So, the voltage, supply voltage will be maintained as equal to the across the armature and across the field winding. Means we can say that the voltage across the field winding will be the voltage V, and I is equal to V upon R. Total resistance of this field winding will be the RF plus RE. RF is the field winding resistance itself, and RE is the external resistance. Overall, we can say that the IF is equal to V upon RF plus RE. Means if we consider a case when there was no external resistance, then the IF was V upon RF. And when there is a external resistance, then the IF is equal to V upon RF plus RE. Means after including a resistance, the current is reducing, and we know this is the very simple phenomena of the electrical engineering. Then with increase in resistance opposes the current and current reduces. So, when we included an external resistance in the field winding, then what will happen? The field winding current will reduce. If the field winding current will reduce, then it will reduce the flux, and if will reduce the flux, then flux will create its impact on the speed. How it will create its impact on the speed? It will depend on the speed equation of the speed. But here it is important to know that after including the resistance, the flux is reducing. Remember this point. And this is the equation, N is equal to V minus IA R upon K1 phi. This is the equation, important equation for the speed control. In this equation, if we create a relation between the speed and the flux phi, then we can say that the speed is inversely proportional to phi, because N is equal to something value V minus IAR divided by K1 into phi. If we do not consider the other parameters, considering there are the fixed values or constant values, then we can say that the N is inversely proportional to phi. And in the previous case, what we have seen? We have seen that with the addition of a external resistance, what will happen? The current will reduce. The current will reduce and the flux will reduce. And if the flux will reduce, then what will the speed? The speed will increase, because the speed is inversely proportional to the flux. Means the overall relation is that by considering external resistance in series with the field winding, we are what we are doing? We are increasing the speed of the motor by reducing the flux. So, this part we have discussed. These two are the important equations in order to understand the flux control method for the DC shunt motor. And considering this, if we plot the characteristics, then x and y axis, on the x axis if we take the speed n, and on the y axis if we take the speed I a, then we know that the speed characteristics, speed versus I a characteristics of a DC shunt motor is a straight line with the negative slope, and speed is slightly reducing. This we have discussed in our previous lecture. So, here the two cases are given, with field rheostat and without field rheostat. With field rheostat, the red color line is shown. Without field rheostat means the blue color line is shown here. Without field rheostat means we are not adding any external resistance in series with the field winding. If we are not adding an additional resistance, then the blue line is the curve, basically the curve, and this is the actual characteristics of the DC shunt motor. And the second, with field rheostat, when we added a resistance in series with the field winding, with the addition of the resistance, what is happening? The current, field current is reducing, field current is reducing, flux is reducing, and speed is increasing. That is why if you see that the complete characteristics curve has been shifted from blue line to upward red line. So, here it is very much clear that the speed control of the DC shunt motor is possible by this method. The pattern of the speed characteristic will remain same, but the speed will get increase. That is why it is mentioned here, Re will increase the field winding resistance, which will reduce the field flux, and reduction in the field flux will increase the speed of the motor. Remember, the field flux motor is what it is doing? It is increasing the speed of the DC shunt motor. That is why it is mentioned here that we can only raise the speed of the motor above the normal speed by using this method. So, what are the advantages and disadvantages of this particular method? The advantage is easy, convenient and inexpensive method. As we have seen, this is a easy method. What we are doing? We are doing nothing. We are adding a external resistance, and by adding the external resistance, we are increasing the speed. It is convenient. It is inexpensive method, as well as the low power loss in the shunt field rheostat due to the small value of ISH. The ISH current, the current ISH is having the low value in the case of DC shunt motor especially. It has this is the low current for the excitation of the field winding. If the current value is low, then if we are adding a resistance in the path of the flow of the current ISH, then there will be power loss, but as the current value is low, so the power loss will be the low. If power loss will be the low, means the efficiency reduction will not be very high, means the efficiency will be maintained higher in the case of the motor. So, these are the advantages, but there are few disadvantages also. Only speed higher than the normal speed is obtained. We can only get the speed which is higher than the normal speed. Speed reduction we are not able to get by this particular method. There is a limit to the maximum speed, as with weak flux the commutation process become poor. The commutation process, which is the very important for the DC shunt motor, it may become poor if we increase the speed of the DC shunt motor beyond a certain limit. So, this is also a disadvantage. Now, coming to the armature control method, the same motor is DC shunt motor, but the method now is the armature control method. Armature, what we will do in the armature control method? We will control the resistance of the armature winding for the control method, as we discussed. This is the DC shunt motor in the diagram. If you see this diagram, in this diagram the armature resistance is connected in series with a resistance having the value of RC, variable resistance RC. In the previous control method, the flux control method, the external resistance was connected along with the field winding, but here in the armature control method, the external resistance is connected along with the armature, because the name is armature control. So, the resistance will be connected along with the armature. So, we can say that the complete armature path, the complete arrangement, the complete we can say the branch of the armature is having the resistance R A plus R C. R A is the armature resistance which is fixed for the machine, and R C is the variable resistance which is used for the control of the motor speed. Now, in this method, a variable resistance RC controller rheostat is placed in series with the armature as shown in the figure. Then the equation will become N is equal to V minus IA R plus RC divided by K1 phi. This is the equation. Remember, I told that this equation is going to become a very important equation for the speed control, and this equation was initially it was N is equal to V minus IA R upon K1 phi, but as we added a new resistance in series with the RA, then it become R plus RC. N is equal to V minus IA R plus RC divided by K1 phi, and IA R plus RC means if we are adding a new resistance RC, then the overall term IA R plus RC will increase. Means we can say that the term V minus IA R plus RC is reducing. If you see that, if you consider here two cases, the case number 1 when the RC is present, case number 2 when RC is not present. If the RC is not present, normal case, RC value is 0, then it will be the N is equal to V minus IA R divided by K1 phi, and when RC is present, then it is becoming equal to N is equal to V minus IA R plus RC divided by K1 phi. Means after adding a resistance, the negative value is increasing because R is becoming R plus RC. So, negative value is increasing means the overall numerator term is reducing. If the numerator term is reducing, then speed will get reduced. In the flux control method, we are increasing the speed, but here we are able to see that the back EMF is reducing, that is the V minus IA R plus RC is reducing the numerator, means it is reducing the speed of the motor. So, considering these important points, N is equal to V minus IA R plus RC upon K1 phi, EB is equal to V minus IA R plus RC, speed of the motor is reduced. Considering this point, we can plot the characteristics between the N and IA. We can plot the characteristics between the speed and the armature current, and this is the speed, normal speed which we plotted in our previous lecture. We have seen that how the characteristic vary. The speed varies with the armature current in such a manner, but this is the without RC case. But if we consider the external resistance RC, then the speed will be reduced. So, this is the characteristics with reduced speed, means the DC shunt motor speed control with the help of armature control method, the speed will be reduced. The nature of reduction of speed with IA will remain same as we have read in the previous cases, but the speed will reduce as we want in this particular case. Considering all these things, we can say that RC will increase the armature resistance, which will reduce the back EMF, very common, and reduction in back EMF will reduce the speed of the motor. And in this case, we can only reduce the speed of the motor above the normal speed. DC motor speed control by flux control method, we are able to get only increment in the speed, and in this case with speed control with the help of armature control method, we are only able to get the reduction in the speed, nothing else. Armature control method disadvantages. Is there any disadvantage of the armature control method? Yes, there are some disadvantage of the armature control method, and we will discuss these disadvantages hereby. First is the power loss is high as it carries the full armature current IA. What we have done? We have connected a resistance RC in series with the armature. If we have connected resistance RC in series with the armature, means that external resistance RC will carry the armature current. If that resistance will carry the armature current, means the power loss will depend on the IA value, and IA value is obviously very high because it is required for the motor operation. basically. So, if the IA value is high and that high IA current value is flowing through this particular resistance, then it will create the high power losses. If the power losses are high, then the efficiency of motor will go down and also give the poor speed regulation. But these disadvantages we will get when we are controlling the speed of DC shunt motor by the armature control method. Due to these advantages, this armature control method is rarely used to control the speed of the shunt motor. Now, but in the case of the series motor, as the poor speed regulation is not important in the series motor, it was important in the shunt motor, but it is not important in the series motor. So, the armature method can be used for the speed control of the DC series motor. Means we understood this particular method of the speed control. We are not able to use this method for the speed control in the case of DC shunt motor because efficiency is going down, poor speed regulation. But as this is not the problem in the case of DC series motor, so this same methodology can be used for the speed control of the DC series motor. Now, coming to the part speed control of the DC series motor. Flux control method. Coming to the flux control method, this is the flux control method. How we will control the flux, how by the flux control method, what results we achieved in the case of the shunt motor. In the case of the shunt motor, we have seen that with the help of the flux control, the speed is increased. In the case of the armature control method, the speed was reduced. Similarly, all these methodologies, the flux control method and the armature control method will be discussed here for the DC series motor. So, this is the diagram for the DC series motor. Having a DC supply providing the current IS connected in series with the series resistance RSE, and RSE connected with the armature having the resistance RA and back EMF EB. EB is the back EMF opposing to the flow of the current. And the new thing here is that in shunt, in parallel with the series field winding, RSE, there is a external resistance is connected here, which is variable in the nature. A arrow is given there, means it is variable in the nature. So, what is happening here, when we are connecting this external resistance here in parallel with this in this particular winding, then what will happen? Then flux value, the value will get reduced. Why it is reducing? Because the RSE and R, basically the overall resistance value will get reduced. It is used for reducing the overall resistance of the winding. Now, coming to the armature resistance control method, what is happening here? In this particular method, what we are doing? We are connecting the series resistance in series with the RSE. In the case of flux control method, what we were doing? We are connecting the external resistance in parallel with RSE, and here we are connecting the external resistance in series with the RSE, or we can say we are connecting the external resistance in series with the armature resistance, because all the resistances RSE and RA are in the series manner. So, because it is the armature resistance control method, so we can term it as the R external is connected in series with the RA. Means in case number 1, we are trying to reduce the overall resistance. In case number 2, we are trying to increase the overall resistance, and considering these two cases, we can control the speed of DC series motor by using the formula, the very basic formula which is required for the control of the speed of the motor. N is equal to V minus IA into R divided by K into phi, and considering this, the flux and the armature resistance can be controlled by using these two methodologies, and speed can be controlled. And as we have done, as we already did in the case of the shunt motor, similarly we can do for the DC series motor also. Now, coming to the next case, which is the Ward-Leonard method. This is also a method for the speed control of the DC motor. Basically, we have till now we have discussed the two methodologies. First was the flux control method, second was the armature control method, armature resistance control method, but the third methodology, which is the terminal voltage control method, we have not discussed yet. So, the Ward-Leonard method, in this particular method what we are doing, we are basically controlling the terminal voltage, and this is the complete arrangement for the Ward-Leonard method. If you see the diagram, there is a generator and there is a motor, and generator and motor both are connected to each other. DC generator is mentioned capital G and DC motor is M. Motor is connected with the load and the G has the output of Vt, and G is also mechanically coupled with the AC motor, which is having the supply of 3-phase AC supply. Apart from this, you are able to see that the two windings are connected, are shown here in the lower part. MG set and DC drive motor is also mentioned here. These two windings, the windings which are not electrically connected with the upper arrangement, is showing that this is nothing but the separately excited DC generator and separately excited DC motor. Means G is the separately excited DC generator, where the RSH is variable as shown here. M is the separately excited DC motor, where the field winding can be the current in the field winding can be varied as shown here, that the externally variable resistance is connected here, and the upper arrangement is in such a way that with the help of the 3-phase AC supply, we are operating a 3-phase motor. This 3-phase AC motor need the electrical input, which is the 3-phase AC supply, and the output of the AC motor is the rotation, will be the mechanical energy, and because this is having a mechanical energy in the rotational part, so the AC motor is mechanically coupled with the generator. There is a mechanical coupling with the AC motor and the generator. When the DC supply, when the 3-phase AC supply is given to the AC motor, then the motor will start. When the motor will start, it will start rotating its shaft, and when the shaft of the motor will start rotating, then it will rotate the generator part. When the generator will rotate, then we know that if there is a relative motion between the conductor and magnetic field, then an EMF will induce. This generator will start rotating, and this generator is having a field winding, separately excited field winding. Then in this field winding, when the generator is rotating, then EMF will induce by this DC generator. This EMF will produce a voltage which is known as the terminal voltage Vt, and this terminal voltage is now given to the motor, for which we want to control the speed, and DC motor is coupled with a particular load for which the motor is designed. Means if you see the diagram, this is the capital M, the DC motor is the part for which the speed control is required, and the remaining left side part of the complete arrangement is required for speed control of this particular motor with the help of terminal voltage speed control methodology. So, with the help of 3-phase AC motor, we can control the speed of the AC motor. With the help of that speed control, we can control the speed of the rotational speed of the generator, and we can vary the terminal voltage. And if we are able to vary the terminal voltage, then speed of the motor can be controlled. It can be controlled above the base speed as well as below the base speed. Because again remember that equation n is equal to V minus Ia into R divided by K into phi. V is the important term. If V is increasing, then the speed will increase. If V is reducing, then the speed will get reduced. So, this is the Ward-Leonard method, which consider the terminal voltage terminal voltage control for the speed control of the DC motor. So, coming to the summary of this lecture, speed of a DC motor can be controlled by 3 methods. What are 3 methods? Flux control method, armature control method, and voltage control method. Flux control method only increases the speed above the base speed. If we want to increase the speed above the base speed, then flux control method will be used. Armature resistance control method only reduces the speed below the normal speed or base speed. If we want to reduce the speed of the motor with respect to its normal speed, then armature control method will be used. Ward-Leonard method, this is the method by which, by controlling the terminal voltage, we can either increase the speed or we can reduce the speed of the motor. So, now coming to the topic which is to be covered in the next lecture, it includes the applications of the DC machines, part 1. Thank you for attending my today's lecture. Thank you so much.